Hey everybody! Today we are going to talk about gradient, ascent, and descent. And these are optimization methods. So, what is the context in which you might use gradient descent or gradient ascent? And the context is when you have some function f of x1, x2, all the way up to xn. So some function of a number of arguments or variables. And you are trying to find the maximum or the minimum of the function. So if f corresponds to maybe some probability, and you're trying to find the most probable set of x's, then you would probably try to find the maximum of f. However, if f were some cost function, and x1 through xn are some parameters of that cost function, then you would be trying to find the minimum. And as you might guess, you would use gradient ascent to find the maximum, and gradient descent to find the minimum. So what's going on here? What does our actual picture look like? Well, as we've realized on many previous occasions, it's hard to draw very high-dimensional functions, but what we can do is to draw a function of two arguments and then claim that all the geometry we're going to talk about and all of the math we're going to talk about holds for functions of more than two arguments. So let's say we have f of x1 and x2. And let's say it looks something like this. So here's x1, here's x2, draw f. So not perfect, but you can kind of get the idea. When f is a two-dimensional function, it will look like some sort of landscape. Now, let's pretend that f is a probability function, a probability density, and we are trying to find the most probable x1 and x2. And that corresponds to the x2 and x1 where f is maximized. So on this picture, you can see the maximum right there. So that's the maximum. And when you see the whole picture like this, it's actually fairly easy to figure out where the maximum is. However, the whole reason we use optimization methods is because generally you don't have access to the entire function. Meaning you can't just see the whole picture and find the highest point. However, what you can do is sample the function at different pairs of x's. What that means is that I can provide the function with an x1 and x2 and see what the value of the function is at that x1 and x2. And if I could do this with every x1 and x2, it would be very easy to see what the maximum of the function was. I would just choose the x1 and x2 that yielded the greatest value of f. However, this is often infeasible, especially if we have a very high-dimensional space of inputs. So what does one do? One possibility would be to choose a bunch of random pairs of x1 and x2 and see which one yielded the highest f. So maybe we would choose an x1, x2 that yielded that f right there, maybe one that yielded that f, maybe one over there, maybe one there, maybe one there. And then at the end of the day, once we had chosen a finite number of random x1, x2 pairs, we would just say, okay, which of those pairs yielded the highest value of f? And we'll say that's the maximum. However, that's actually not going to work very well. And you can probably see why that's true based on this drawing. When you're just randomly sampling, you're using no strategy to try to figure out where the maximum might be. You're just choosing randomly. So can we do something a little bit better? Instead, we're going to use a method called gradient ascent. And how gradient ascent works is that you pick a starting point, and then instead of just randomly moving to any other x1, x2, you instead move to an x1, x2 pair that is in your little neighborhood. So you only move to points that are nearby. So this is very similar to what you would do if you were maybe in a foggy city or in a city at night where you couldn't see very well, and you were tasked with finding the highest point of the city. You obviously can't randomly jump around to take different samples of different points of the city. Instead, you can only move locally. All right, so now that you're constrained to only move locally, to only be able to move to locations very nearby to where you currently are, well, if I were trying to find the highest point in the city, what I would do is I would always walk in the steepest direction. So to find the maximum, walk in the steepest direction. So if I started right there, the steepest direction would maybe be that direction. So then I would take a step of a finite size to over here. And then when I got there, the steepest direction might be that way. And then I would keep going, and keep going, and keep going, and keep going until I got to the top. And how would I know when I got to the top? Well, every direction would be equally steep, and the steepness would be 0, because it would be completely flat in every direction. So hopefully that makes sense intuitively, and in fact, that is all that gradient ascent does. Gradient ascent is just the method of finding the maximum of a function by starting at a given point and always walking in the steepest direction. And so why do we call it gradient ascent? Well, it has to do with what kind of calculation we do to find the steepest direction. And so let's introduce the notion of the gradient. So that's our symbol for the gradient, a little upside down triangle. And so if we were to take the gradient of f, that is just equal to df dx, df dx1, df dx2, and so forth, all the way to df dxn. So the gradient is a vector, each of whose entries is the partial derivative of f with respect to one of f's arguments. So if f has n arguments, n inputs, then the gradient is an n-dimensional vector. And there's one other very special thing about the gradient vector. And this is that it points in the steepest direction. So if you picked a point, maybe we were back on our function, we picked a point right there, and we were to calculate the gradient of that point, we would find that the gradient, which is a 2D vector, would point in the steepest direction at that location where we started. So this is really nice. By calculating the gradient, we know which way to go if we want to go in the steepest direction. And so how the algorithm for finding the maximum of a function would proceed would be you pick some starting point, so x1, x2, we'll call that 0. That's your starting point. And then calculate the gradient of f at x1, x2, sub 0. So the gradient of f evaluated at x1, x2, sub 0. And so that tells us the direction to move. Now, to implement this practically, we have to take a step in that direction. And we'll usually choose some finite step size. So we can call this alpha as the step size. So if we started at x1, x2, 0, and we're trying to find the next point to sample, how do we do that? If we take one step in the steepest direction, where will that leave us? So what does x1, x2 sub 1 equal? Where we are after our first step? Well, that's just where we started, x1, x2 sub 0, plus the step size, alpha, times the gradient. Not too bad. What about the next step? Well, we calculate the gradient at x1, x2 sub 1. And then our next step leads us to where we were previously, so x1, x2 sub 1 plus alpha times the gradient, the new gradient. So if you're doing this right, the gradient might change as you move to different locations. And so this is the algorithm. At each point, you take a step in the direction of the gradient, which is the steepest direction, and that step size is alpha. And so you can keep on doing this over and over and over again. And then when do you stop? Well, you stop when the gradient of f, so after the kth step, you stop when the gradient is equal to 0. And this is because the magnitude of the gradient is equal to the steepness of the slope. So if the gradient is very large, then you have a very steep slope. And if the gradient is 0, then you have a 0 slope. And what does a 0 slope mean? Well, that means that you've reached a maximum. So that's how gradient ascent works. You pick a starting point, and then you follow the gradient to the top. This can have a few problems, unfortunately. So in this picture we've drawn, for example, which peak you reach will depend on your starting location. So if we started here, we'll probably reach that peak. However, if we start somewhere over here, we will reach this peak, which is a local maximum. So if your goal is to find the global maximum of your function using gradient ascent, it's usually a good idea to run the algorithm a few times from random starting locations. And each time you run the algorithm, you will get some final x1, x2, all the way to xn set of inputs that yielded a local maximum, or that caused the gradient ascent algorithm to stop running. And so for each time you run the algorithm, you'll have a set of these x1s through xn's, and then all you do is pick a set of x1 through xn that yielded the highest value of f. So that's it. That's the gradient ascent optimization method. If you're trying to do gradient descent, so maybe trying to find the minimum of a cost function, for example, then you're just walking down the hill. So you do the same thing as in gradient ascent, but you go in the direction opposite of the gradient. And again, you keep taking steps until the gradient reaches 0. And again, we've gone through our examples in 2 dimensions, so with 2 arguments for our function f, but the same general idea holds for higher dimensions. So for when we have x1, x2, all the way through xn. The gradient tells us the steepest direction, and we just walk in that direction until the gradient is equal to 0. And when the gradient is equal to 0, that means we are at a maximum or a minimum. And that's it. This is just one of the many optimization methods there are for optimizing a function of many arguments. And in many cases, it works pretty well. So if you're trying to find the ideal network weights for a feed-forward neural network that you're trying to use to do classification, for example, gradient ascent does a pretty good job. However, keep in mind that it is not the be-all, end-all solution. There are still many varieties of functions which are not maximized particularly well with gradient ascent. However, one good check to see if gradient ascent is working is to pick a bunch of random starting locations, and if they all converge to the same maximum, then that suggests that f is actually fairly well behaved and may have a global maximum that is relatively easy to find. All right, and that's it for gradient ascent and descent. Thanks for watching.